training for this.
Good afternoon. Welcome to the CERIAS Security Seminar at Purdue University. It's my great pleasure to introduce today's speaker, Trent Jaeger from Penn State University, where he's a co-director of the Systems and Internet Infrastructure Security Lab. Before joining Penn State, Trent was a researcher at IBM Research for 9 years, and his research interests include operating system security, access control, and software and policy checking. And today Trent will talk about system-wide integrity.
Yes, so I'm going to talk about a big problem. Welcome. So the security community has developed a number of techniques for trying to protect our systems. But what we're finding is these techniques are rather ad hoc at present. And so what I'm going to talk about is trying to pull these different approaches to protecting the integrity of running code and overall protecting our system into one coherent paradigm. Okay? So what we have currently is, unfortunately, basically the same situation we've had for a long time. So this is the list of the SANS top security risks. So SANS is one of these vulnerability collection outfits like BugTrack and so forth. And so as of September 2009, what they were identifying was that these were the big problems. They were saying application vulnerabilities were exceeding OS vulnerabilities. Basically, we're pushing, the attackers are pushing their attacks into in particular web applications and utilizing the fact that web applications run with authority to manage data that's both security critical and untrusted data, and they use this to be able to take over these processes. So what we're also seeing is we're still seeing a lot of basic attacks like buffer overflows, things that we've been seeing for nearly 40 years. And what we're also seeing, zero-day attacks are continuing to increase. So what we're seeing is that attackers are getting better at launching attacks against our systems. Things like just signature checking on input is not going to be enough to ensure the integrity of our systems. Attackers are getting better at evading these kind of systems. Okay? So what we're going to need is not to add more ad hoc techniques, more little techniques to defend from attackers, but we're going to need to think about some more radical approaches, some approaches where we can get the edge on the attacker, where we can understand what it is that defines the integrity of our system and use this to dictate to the attacker where threats are and to be able to track what the attacks are in the system, what the potential attacks are in the system, and track whether they're being leveraged. Okay, so let's look at an example. So this is sort of a typical attack of recent times. We have a web browser. It receives some malicious web content, and that content is then run by some plugin, and the plugin has some vulnerability. Okay, so browsers are not just one individual program, but a whole set of programs all melded together, and some of them may have vulnerabilities. Now, the attacker is attacking this web program, which is a little bit, or this browser, which is a little interesting because the browser doesn't really run with privilege, right? It just runs with your permissions, with user permissions. So it's an unprivileged process. So attacking this doesn't get the attacker as far as attacking, say, a network-facing daemon, some root process that's connected to the network. So what we're seeing is the attackers have beaten these root processes pretty much to death, and we've done some improved defense on those. And now we have this other vector of attack, which is through these unprivileged processes. And once the attacker can compromise these processes, they can launch what SANS simply refers to as a local exploit, implying to me, and this is also my understanding from a number of years working in this business, is that there are a lot of different ways the attacker can knock over your system once they get a hold of even an unprivileged process. They can then use local exploits to compromise other root processes on your system, get control of your system, and then start to do some more bad guy stuff. Okay, so the bad guy stuff that they're doing in this case is they're getting access to some files on your system that have authenticating information, in this case a password file. So the password file may contain the password of the administrator, not only of an individual system, but of the whole domain in a Windows domain. And if that's the case, then they would run a password cracker such as John the Ripper on this. I was thinking Jack or John. This John the Ripper on the password file, and then they can knock over the whole domain. Okay. So what we're finding is these are the same old problems that we've been fighting for many years. The attackers move around, new applications are introduced, new problems are introduced, new types of vulnerabilities are found. The attackers are improving their means for delivering malware and hiding their exploits from the defenders, us. So what are we going to do? So what we want is a coherent approach to system integrity. Currently we have a rather ad hoc approach. I'll talk about that more specifically in a minute. But let's look at what the individuals are doing. This is actually kind of interesting because historically, from a security perspective, usually we think of security being the job of the system administrator. We have the system, we deploy the system administrator configures it and makes it secure. But systems are way too complicated for system administrators to do the right thing. They're even too complicated for system administrators to put together the systems themselves to function. Basically, what we have are programmers writing code, and for a long time, I started a long time ago working on computer security, and we told people a long time back that if the programmers just program securely, things would be okay. That was our mantra back in the 90s. And so what we found is, in my opinion, we haven't done a good job of telling programmers how to program securely, what tools to use to program securely. Do you know how to program securely? Anybody? No? Me neither. So what we need is to come up with techniques that will help the programmers do the right thing. Now, programmers build their programs, and now in modern operating systems, you'll have some means of deploying these programs as a unit. Not just the binary, but supporting libraries and other files will come together with that program and be installed on your system, and you can then run them. So this all is configured by the OS distributors with the program. That's figure out which programs to run on your system is determined by the OS distributors. And OS distributors now also figure out what the default policies are. So for Windows systems, you have access control lists, and what these are initially is influenced by the OS distributors. There's mandatory integrity controls, which are in Windows, that are determined by the Microsoft people. And you start from there, and then you start to mess with your system. In Linux, it's the same kind of thing. You have what are called Linux security modules, either AppArmor or an SE Linux, and these are configured by the OS distributors, and then you just run your Linux system and hope that they did the right thing. Now, SE Linux has quite a few, tens of thousands of rules, and so this isn't something that you are going to be able to modify. You're depending on the OS distributor to do the right thing here, and they're trying to do the right thing. Next, the system administrators get all of this. They get all of the programs, they get the operating system distribution, and they try to put this together. Maybe they get a bunch of them. They have a bunch of machines that they need to administer. And they're going to get these and put them together into a system. So the job of looking at the OS distributions, what all the packages are that are installed, whether the policies are all right, whether the programs have bugs in them, this is way beyond what the system administrators could possibly do, or anyone could possibly do in a reasonable amount of time. So what they can do well generally is manage the network. They can write firewall policies. There's still some potential for error there, but that is sort of the maximum we could expect from them. So we can't get a handle on attacks until we think about how these people do their jobs and how we can provide tools to help them do their jobs better. So some recent excitement has come about due to cloud computing. And in cloud computing, the big risk big concern that people have is data security. I'm going to take my security critical data and run it on somebody else's systems owned by somebody else. And so, you know, some of you may have done this already quite a bit, running, you know, various services and applications that are run on the cloud. Facebook was run on the cloud for a while. Now they're building their own data center. But, you know, for folks that have real high-value security critical data, running this on the cloud is really a scary proposition. Now, while data security is a secrecy problem, the problem comes about largely because we can't get a handle on integrity. For example, we wrote this paper in, I'm supposed to move the mouse around here. This paper here, and that's at this link talking about security in the clouds, and that the problem is related to lack of control and the lack of visibility about what's going on in the cloud. And so what we're seeing are concerns because we don't trust the hosting environment, for example. The cloud vendors say they're working hard, but we don't really know what's going on. We can't see what's going on. When we lose control over what the hosting environment does. We don't know whether their insiders have access to our data or not, how that's protected. I'll talk about how we would install systems to prevent these problems. The second problem, we don't trust other computation on the cloud. You know, it's sort of weird if you're used to running your jobs, you're a business, you run your jobs, you run them on your data center, and now, you know, you're Pepsi and you're running your job on the same cloud as, same node as a Coke job. You know, this is an unusual thing, but this is something that could possibly happen now with cloud computing. We don't trust other processing, and we also, looking at the third bullet, don't trust ourselves to protect ourselves from this processing. There's a lot of concern about covert channels, but I think that's an issue with respect to resource management that also could be made more visible and dealt with better. Even though it's a secrecy problem, we could still provide high integrity control over what's going on to protect, to defend against covert channels without adding a lot of complexity to our system if we looked at it in terms of integrity. Okay, so what we want to do ultimately, so this is our long-term goal. We're not going to get there by 520 all the way, but we're going to move toward it, is to develop scalable and automated methods for computing policies that protect the integrity of our individual components. And in addition, we can do this not just for the individual components, but for the whole system at large. All right? So we have this lofty goal that we're going to have some methods that will be able to represent our system consisting of multiple independently developed components, and that we're going to be able to assess integrity protection in that model and be able to fix our policies, generate policies in the end that will satisfy some integrity goal that we have in mind. So, how do we protect integrity now? Anybody? What's a way we protect integrity? How do you protect integrity, sir? Firewalls. Mm-hmm. That's right. Those are good things. Encryption. Uh-huh.
Watermark.
Sorry?
Watermark.
Watermark. That's getting serious in terms of integrity. Most people probably depend, on somebody else. Okay, so there are a few different ways. So we might define. Really, the OS distributors are defining for you a policy aimed at least privilege. They're trying to define policies that limit processes that are running on your system to use just the permissions that they have in mind. Okay? So you guys familiar with least privilege as an approach? Okay, good. Others might sign their code, hash and sign the hashes of the code in order to check the code integrity. When you download distributions, you can get these code signatures and you can check them. They're not really used quite as broadly as we would like, but that's another way. These access control policies on Linux, Ninghui studied the confinement of network-facing daemons by the AppArmor and SE Linux systems. So the idea is these root processes that before were getting knocked over and then enabling the attacker to take over your system, these had full root permission, had full access to your system. And so the folks in the Linux community defined these policies to restrict access of these processes to your system. So if they were hacked, if they were compromised, they wouldn't be able to install a rootkit on your system. Now Ninghui found that these policies aren't really comprehensive, that there are different numbers of network-facing daemons that still have access to effectively to permissions that can enable them to knock over your system, but some of them have been confined anyway. So we try to use this. We mentioned firewalls, input filtering. So the Department of Defense certainly uses a lot of input filtering on their external networks to try to test what's coming in and try to detect bad stuff before it gets into their networks. This is getting more and more difficult because the attackers are getting better at designing their malware so that they can get by these scanners. And then we have application-specific techniques. So there's stuff now like PAX and StackGuard to prevent buffer overflow attacks from happening in your system, even if you happen to have a poorly programmed system that would normally be susceptible to such attacks. Okay? So we have these different techniques. They are all valuable techniques, but we don't really have any plan for how to put them together, right? They're all different techniques. They're different levels of the system. They provide different forms of protection, and if we apply them all, and we apply them all perfectly, is our system secure? Is it integrity protected? Can we prevent an attacker from getting into our system and taking over? No, we can't. We don't really know what all of these things together mean. So, do we have any principles that we can leverage for this? And, well, the answer is people have tried to develop principles for this. So back in the 70s, people developed, Ken Biba wrote this report, and he defined 3 different models of integrity called, the Biba integrity models. One's a strict model, one's a low water mark or LOMAC, and then one is called the ring model, which is similar to the mandatory integrity that Windows uses now. So you guys familiar with Biba integrity? 1, 2, a few. Some don't want to admit it. Fair enough. Okay, so this approach is one way, and then we have about 10 years later, David Clark and I forget Wilson's name off the top of my head, developed an integrity model, trying to better model what's going on in real systems. So the advantage of Bella Padula for secrecy is that people already use these secrecy levels and already controlled the distribution of documents in a paper form that way. People were used to doing that, so if we computerized it, great, people could use it. We have it makes sense in the real world, which is a good thing. Now, Biba didn't correspond to anything in the real world. He just, reversed Bella Padula and said, hey, look, that might work. And people tinkered with it a bit, but they really couldn't figure out how to make it work effectively. So Clark and Wilson looked at integrity in the real world. Are you guys familiar with that model? That's much less well known. Ninghui is, that's good. And so this is a model that's looking at how integrity might be satisfied in a business sense, in an accounting sense. Okay? And later I'm going to talk about these practical integrity models a little bit. Probably won't have time to go into them in too much detail. Ninghui's responsible for the UMIP work. I don't think anyone here was on that paper that's in this room now. Yeah. And so Shekar at Stony Brook did PPI. We did the CW Light work, and then there's some work out of MIT and Stanford on this decentralized information flow control, DIFC. And so all of these are trying to make Clark Wilson and Biba real. So what was Clark Wilson about? Well, common sense says you want to start with a high integrity system. So they said, hey, in the real world, you want to check that you're starting with good stuff. And so in an accounting sense, you're going to check that the data that you're using satisfies an initial verification. So in accounting, you actually do double bookkeeping and things like that to make sure all the numbers add up, 2 different ways, so you know that things are good. So then they also use specific, so once you set the baseline, then you want to only do updates through trusted processes. And so they have their own names for this called transformation procedures. Now, both transformation procedures and these initial verification procedures or integrity verification procedures have to be formally assured in order to be part of the model. In the 80s, we thought this was going to happen, that we'd have formal assurance tools. We'd take our program and throw it in the tool and crank it out, and we get, yeah, it's good sort of answers. But this sort of methodology hasn't really scaled yet. We're seeing some things come about now, but we still have a ways to go. And then we're going to run our system with these transformation procedures, make sure they do the right thing, that they can receive, in Clark-Wilson, they allow these procedures to receive untrusted inputs and either discard them or upgrade them. So unlike BIBA, that doesn't really allow any untrusted inputs to go to your processes that may be high integrity. Clark and Wilson do allow it, but they require formal assurance. So neither BIBA nor Clark-Wilson, despite some efforts, have found practical application yet. And so we're going to need to look at this in more detail ultimately. So what I'm going to talk about is an approach that I heard about last week. But I think it corresponds to the approach that we're already trying to make, and so it's a nice way of describing it, I think. So I'm going to try to describe it kind of sort of in their way. We'll see how it goes. So Flieger and Cunningham, I believe it's in this paper. Now, I just saw the talk from Rob Cunningham, and I couldn't download the paper when I tried to download it. So I believe it's this paper, Why Measuring Security is Hard. But from the talk, what I learned is that, hey, you should start with the specification of security, that you should start with your system specified so that, and tested so that you know, okay, this is the way the system can run and be secure. So you're going to go to a lot of trouble to set up your specification. Then you're going to install your system in such a way that specification is met, and you can bootstrap the system, check your integrity like a Clark-Wilson integrity verification procedure, and then you're going to run the system to that specification. So I was going to talk about all three because we have some work in all three areas, bless you, but there's no way, well, I don't know if I'll be able to make it anyway by 5:20. So I'm just going to talk about installation and specification. And I'm going to talk about installation first because it's a lot easier than specification. We know more about that. And I'm going to try to hit specification and give you an idea of where we're going with that and try to give you some ideas for where you might be able to take it. Okay? So installation, we actually have some work on this. A few years back, the hardware support, a hardware component was added to systems, to most of your desktops and quite a few laptops, called a trusted platform module. And so the idea was with this hardware, we could then measure the integrity of a particular system. So what we could do, for example, and what a lot of people did, is measure what code is running on the system, and so get a sense of, okay, that this code is actually satisfactory. And they would check this well, they would measure it at runtime, and then a remote verifier would do the actual verification. So the TPM doesn't enforce this kind of integrity, but enables it to be measured. Now, that's not entirely satisfactory, because you're just checking the code at load time. You don't know really what data is going into your application or where this came from. And so you have sort of an incomplete picture of the execution of individual programs. So this later work on Flickr out of CMU, and they have some subsequent work, what it does is it looks at measuring the computation. So they use this hardware that's now available in Intel and AMD processors called a dynamic root of trust measurement. and they basically, you're running along. So the idea of this hardware is you're running whatever garbage you want, whatever crazy, unsafe stuff you want to run, go for it. But then when you want to do a high integrity computation, you trigger this dynamic root of trust measurement. I think it's supposed to be DRTM, and this will basically, separate your computation from the rest of the system. And so with Flickr, what they do is they provide the input data and the computation into this DRTM triggered environment, and that environment then is isolated from whatever crazy stuff you have running. And that computation will run till completion, and then you'll be able to get certification of that computation. So it's kind of a neat little thing, but it only runs for a very small computation. So, and you have to stop everything else. And so what we'd like to do is use similar techniques, but be able to install systems that hopefully meet this specification, and be able to run them for a long time, not just run one little computation after, at some arbitrary point. So I'm going to breeze through. I'm going to go through this a little bit faster. The work that we've done, published in ACSEC, and we have a couple papers in this Security and Privacy magazine. So I'm going to skip this slide. So the two defenses that we're looking at are data. So there's actually, not only do we care about code, but we also care about data. We care about configuration files. We care about keys. We care about, whatever sort of data you're going to use in your computation. So we want to make sure that that data corresponds to some known value. So I'm talking about data, not the input data to the process so much as the data that comes with the package when you install it. Okay, so more the configuration-oriented data rather than the data that's going to be used for processing. Administrators also we have problems with. So we're talking about insiders in the cloud. Administrators could do malicious things, or they could do ad hoc things. And either way, we're sort of unhappy with that. And so what we'd like to do is get all of the administration done from outside the system, install a system to that administration, enable you to then verify that the root file system that has all of your programs and configuration files, that all of that corresponds to what was installed in the first place. So we developed this notion of a root of trust installation. So what was kind of interesting is the question of whether this would actually work, right? So the idea is we're going to install a bunch of programs, and then we're going to take the hash of these programs, and we're going to then store that hash somewhere and check it whenever we bootstrap the system. And the question is, well, doesn't the root file system change? Will that really work? Can we assume that it's going to stay fixed? And so what we found is for the privileged VM of Zen, that the root file system changed very little. There were 3 files that changed, and each of those we envisioned that we could handle in some sort of ad hoc way. Most of this stayed consistent. And so this idea that you could install a system, no user accounts to the root VM at all. You would configure it all from the outside, no manual input for installation, and then you could check it later each time it runs that it's still the same system you would expect. Looks like a practical thing to do. Now with this we installed from DVD, which isn't totally, so we did this with Debian and used the TPM. So we installed from the DVD, which isn't entirely satisfactory. If you were running a data center these days, you're not installing systems from DVD, right? That's way too painful. What you'd like to do is sit at your desk, kind of like this one, I guess. This is a nice desk. And with your computer monitor, and you might have a web application, and the web application maybe shows you that every system in your data center is installed as you expected. And if something weird's happening, you would then see it. The attestations would come back wrong. So the idea is that the RODI proofs would be sent to your machine, and you can verify that everything corresponded to what you expect. So in the cloud, they usually use a network-based installer, such as Pixie Boot, and there are a number of attacks that can be performed against that, either on the individual components by messing with some of the firmware on those components, or if any computer in the data center gets knocked over, that can start responding to DHCP requests and and then eventually provide bad stuff. And of course the content may get messed with in other ways. So we want to be sure that it works on the in network install as well as a DVD install. So we define this sequence of steps, which is similar to the Rode approach, although I've outlined it in more detail here. The red phase, the gather phase, is actually untrusted. You just go out to the network and gather whatever, and the system then is going to use trusted code to build a proof of whatever it was you installed. So if you installed bad stuff, then you at your desk with your feet up will have to actually, maybe get up and do something. And but otherwise, you can kick back and play Farmville or whatever it is the system administrators really want to do. Let's see. So the other good news about network install is that it's actually a lot faster than the DVD install because the network bandwidth is better. So this takes about 90 seconds to install a Linux distribution on a system, which is pretty nice, as opposed to it was about 8 minutes, I think, from the DVD. So it takes about a minute to set things up on the TPM, but you only have to do that once. In addition, in this case, we're using the DTRM also, or DRTM, I should say. So if you do subsequent updates, you could send those also over the network and build proofs. So even if you're going to do actual updates, you don't do them in an ad hoc way. Every update corresponds to a Rode proof. So you aren't stuck with one installation. You don't have to always install from scratch necessarily, which is nice. Okay. So now, are you ready to, if we installed our cloud system this way, would you now use it? That is, if your specification for the cloud system satisfied your goals. So that's sort of the question you need to think about to yourself, or and we need to think about as well. What else might we need to do? So what we ultimately need is to figure out how to design a system that's going to satisfy specification. And so I'm going to give you a little bit of a broad brushed and a deep dive into policy specification. So this may sting a little bit, but hopefully it'll make sense. Okay? So what we want to do is actually generate access control policies that satisfy integrity goals. And so we have some maybe high-level integrity policy, and we want to generate access control policies for all of our components that will satisfy that integrity policy. So I meant to use policy twice. It seems sort of redundant. It's like, well, if you have a policy, why would you want to generate another policy? You have a policy. Well, these integrity policies would be sort of high-level, BIBA, Clark-Wilson sorts of things that we haven't yet been able to achieve. And we want to convert those into the actual Windows, Linux. There are even enforcers now for virtual machine monitors. Zen has some enforcement mechanisms, as well as a number of program-specific enforcement mechanisms. We would like to be able to push whatever those policies are into those components and be sure that they enforce something that's an approximation of BIBA or Clark-Wilson. So this is based on some work that we've done over a few years. So let's think about the browser and web applications in general. So the browser is really like a little operating system, right? And at least, and now it is a little operating system in things like Chrome and OP. So you have a number of computations going on. And they each may have different security requirements. You may have untrusted stuff being run alongside of your key, banking applications or security critical applications uploading files to your business or what have you. And so all of these are run in components in the browser, and then on the other end you have the web server as well. So we're going to look a little bit at these guys. So people figured out that, hey, there's some problems with this. The attackers helped us out there in that regard. And then we started to think about, well, how would we defend against this? And so we went through the cycle that actually happens all the time in the security community. I'm sort of hoping someday it'll end. But we start out with a new program, great whiz-bang thing, cool functionality, great fun. And then attackers start breaking it. And then we start doing some ad hoc changes, some tweaks to try to get it to be secure, and then we end up breaking down and building something called a reference monitor. That is an enforcement mechanism that achieves these reference monitor policies. So there's the Anderson report from way back in 1972 that you should all at least be able to cite and understand whether a particular component meets that or not. So so we went through that with the browsers. Oh yeah, and then we build a reference monitor, and then the policies get too complicated for anybody to use. So we did this for Java, and we're doing it for Android now, and the browsers in another case. Linux and Windows both have nice reference monitors. Windows still has a DAC policy, I guess, and so not a pure reference monitor, but they have a nice enforcement mechanism. But no one really specifies these policies because they're too complicated. So that's another reason why we need to generate them. But interestingly, people started adding security for the browser at all sorts of different levels. So I believe the order was the browser work was probably first, and then the VM isolation was second, and then finally the process isolation was third. So what we have is enforcement at all these different levels. We could use enforcement within the browser, within the program itself, and a number of different techniques were developed for this. We could add enforcement at the operating system level and isolate individual processes. Or we can use VMs, put a browser in a VM and isolate that VM from the rest, from the bad browser VM. All of these things are possible. And so you might want to have some choice over which of these mechanisms to use, and you might want to create policies that manage how you're going to deploy your web application at each of these layers. And so we built a prototype to do this, but we had to specify all the policies by hand. So we, being my graduate students, specified these policies by hand, and they're sort of experts in defining policies for SE Linux. And then we had our own browser. Actually, we didn't use a standard browser, so we were an expert in that because it was our thing. So this isn't the sort of thing that you'll be able to do that you'll expect a system administrator to do, right? They won't be able to specify a policy at all of these levels for each deployment that they're going to create. We need to be able to generate these policies. So this is another picture, I guess. This goes with what I was just saying, showing you the different policies at the different layers and talks about the problems that we had to solve. So, let's see. So we have these practical integrity models, and there are a few different ones. And I didn't know, I probably should have taught you UMIP since I'm at Purdue, but we haven't built anything to that yet. So I'm going to have to talk to you about this DIFC stuff. So there are a few papers on this decentralized information flow control. If you're interested in it, I would look at the Flume paper. I believe it's SOSP 2007. The paper is very dense and takes a few reads. I've taught it in class a few times, and it generally takes a couple class sections to get through the whole thing because there are a lot of concepts there. So I'm going to give you sort of the watered down version a little bit. So the idea is we want to enforce information flow integrity, but some of the processes have authority. So in BIBA, only fully assured processes have authority, and they have full authority. In this case, we're not going to say that a process has full authority. It has some authority. So it might be able to receive some untrusted data and upgrade it. And it might be able to send some, it might be able to prevent sending some bad data to some other guy. But, we're not going to say that it has full authority necessarily. So they're going to propose this information flow model to express this, where they have exceptions to, which are called capabilities in their model, to express when they're going to do something that would violate BIBA or Clark-Wilson. So the policy model at the base isn't very complex. For each integrity classification, you could sort of think of them as categories in multi-level secrecy. You have a tag. So you say, okay, well, I've checked this data against this integrity property. I've checked that data against that integrity property, and so forth. And so the data might have a set of tags that represent the things that you've checked. And a label of the data is then just a set of tags. And so we then label our processes and resources, and we let things fly. And Flume will authorize accesses based on the labels of the individual processes, and then these exceptions or capabilities, they call them. Okay, so it's similar in spirit to these other models that I mentioned. It's sort of opposite of UMIP in the sense that they try to keep their integrity high and then use exceptions for the cases that they're where bad things happen. Whereas other systems, UMIP describes things will go down by default and then uses exceptions to say when things will stay high. Anyway, that's my conversation with Mingli. Okay, so we wanted to define a model that would enable us to reason about information flow and then ultimately generate these DIFC policies. So we came up with this approach after many generalizations. So basically, we treat the system as a set of data flows. And turns out getting data flow for an entire system isn't as hard as one might think. We actually have a lot of information about this, and we know how to compute these things. So we know how to compute data flow for programs pretty well. We know how to compute data flows from policies already, such as SE Linux, and these other policies for virtual machine monitors are very similar. So we can compute all of the ways data could flow through the system, and we can. An issue is how abstract we want to do it, but let's just assume that we're going to deal with data flow between individual subject types or subject labels rather than individual processes or individual files. Ultimately, I'm not going to describe what the objects are. It doesn't really matter that much, so I probably shouldn't have said anything. So once we have the data flows, then we're going to have imports. So we're going to introduce data to our system. We have the data flows, and what data is actually going to flow depends on what data you provide to the system. So here I'm using data very loosely. It might be a program. You might introduce a program that's of a certain integrity level, or a piece of data of a certain integrity level, or you might, get some data from the network, and that would be low integrity, and you might get, your security critical data that you want to protect, and that would be high integrity, and you might have the kernel, and that would be higher integrity, these sorts of things. So you import some data into your system, and you can imagine it flowing through your data flow graph from wherever it starts. Okay, that's the image you should have in your mind. I'll show you some pictures in a minute. And then we have an integrity lattice. So this is the policy that should be met by the system. So if the system is ideal, it would satisfy this integrity lattice. So this would be like a BIBA policy. So we're not going to exactly meet it. We're going to have some exceptions. And then we have this this long word, intransitive flow constraints, and those are our exceptions. These are the cases that we deal with specially in these other policy models. Okay, so in a safe system, what's going to happen is that all the information flows that result from our data flows with the imports that we have will satisfy the integrity lattice, given constraints. So the constraints might block some bad things from happening, and thus we might have a safe system. Okay, so for VM systems, we end up with this hierarchical picture here, where we have at the top is the VMM policy. And so this shows the data flows among the VMs in the system. And then under the VMs are under the VM dots are the individual policies of the VMs or their operating systems. So Windows or Linux policy is in the middle. And then individual programs might also have their own policies, or maybe where we have insight into their data flow graph and we use that as their policy. Okay? And you can then connect these things together. It turns out that for each of the components to speak to one another, they actually have to go through these, I don't know if you can see them, these very thin lines that connect. So if you have a process in this operating system here, in order for it to talk to this process over here, it has to go through the virtual machine monitor, be authorized by that policy, and then go back in to this. And so we actually have these points of enforcement, and so the information flows actually end up looking like as shown here. So the program analysis people actually look at, if they see this kind of thing, they think, hey, this is like a program, right? You have the main routine at the top, and then you have other subroutines, and then other routines. So they actually have data structures for expressing this that we use. There's something called a hierarchical state machine, and there are actually other ways of representing this. So we can express this in a known model. The difference is that the calls in this model, these thin lines, are a lot different. There are a lot more interactions that are possible than in a program. usually you have one way to call a subroutine, right? One API. But in a system, you might have lots of different paths to lots of different parties that you might interact with. But the models can still, they're general enough to support that. Okay, let's see. So we use this model. I already said we know how to build data flows, so I'm going to skip this. But we built a number of tools. I forgot the name of your tool, but I wanted to include that also. So now imports. So the idea is, in this data flow graph, you'll introduce some data at some node, and based on the edges that you have, it'll flow around, right? So that seems easy enough. Of course, you might introduce data in multiple places of different types. You might introduce trusted data and untrusted data. So some process might listen to the network, and some process might have your financial information. And if you just push them around the data flow graph, there's a good chance, without any constraints, that these parties are going to meet at some point, or this data is going to meet somewhere. And it may meet in a lot of places. And where it meets, you're going to have to deal with this, because this is going to be a case where you have a process, or some component, depends on what level it meets, some component that's going to have authority to both protect your valuable data and receive this untrusted data. And so you're trusting it with the authority to handle these things in the right way, okay? And so what are you going to do about this? Now, this introduces a deep conceptual problem that I'm just going to touch on here, because I have 2 minutes and 40 seconds, called label inference, where you're going to, when two data of different types meets, how do you infer what the result is? You could either, what's traditionally done is you assume that you're going to take the lower bound of those. That, hey, you have bad data, good data, you mix them together, you have bad data, right? So sewage and wine, you mix the sewage, was it a vat of sewage, you put in a little wine, it's sewage. Vat of wine, put in a little sewage, it's also sewage, right? So it goes down. And that's the default way of doing it. Now we're going to do things a bit differently, and DIFC also does reasons about things more in this way. People sort of are programmers, I think, have been optimistic about their programs. I built that program, it's great, it's going to protect the integrity of my system. And so it's going we're going to assume that the programs are going to try to do the right thing. And you're going to have to explicitly say, no, it's not really protecting the integrity of all the inputs, it's receiving the inputs, but it's, it's going to only protect integrity up to maybe a lower level, okay? So we'll make this explicit, and we'll try to reason about these sorts of things in our model. Okay, I'm not going to talk about safety. Eventually, when these things meet, if you decide that your program is not going to be downgraded, then you have to deal with these exceptional operations, and you'll need some kind of superhero-like thing to ensure that things work out. And it turns out that there are only two types of exceptional operations that we deal with in the model. They're very general, two very general approaches. I've spoken about downgraders, so you explicitly say when you're going to downgrade data by defining a level, and all the data above that's going to be downgraded to that level in your system. You're not going to protect higher integrity data. So if you're a normal user process and you receive data from the kernel, you're not going to protect the kernel's integrity necessarily. You say, okay, I'm just a user process, downgrade me to that. And then we have enforcers, and so the idea is an enforcer is going to determine what kind of data is going to be sent to what other parties. And so if you have, say, a privileged VM, the privileged VM will receive inputs from all of the guest VMs, but it's going to generally be trusted to isolate these, so it'll only allow the data to go to the individual guests that were provided by the guests. So there's some enforcement that you're depending on, and we make that explicit in this model. Okay? So we built a tool. You can then reason about what's going on, and you can see which ones are safe. Safe are green, so not very safe here. And red is unsafe. And then the enforcers are the circle to the right that's white. So we have, I wouldn't expect you to be able to read this, but we do have a system. And we do these analyses that I was talking about, and we find things that are, we find errors, and now we want to fix them. So what do we do with the tool? So So what happens at 5:20? Okay. I'll try to finish up. So, so what we can do is we can infer we build this data flow model, and we want to figure out where some constraints are. And so we can infer some of these. There's some sort of obvious behaviors like the privileged VM. We think, okay, this guy has to be an enforcer because it's receiving all of these inputs from all of these parties independently. And these parties aren't talking to each other directly. So we're depending on that guy. So we can infer some things. We can then, based on that, so we have the lattice model, the imports, those have to be specified manually. We determine some constraints, data flow we could compute. So we'll detect where bad things can happen. And so we call these attack surfaces because these are places where programs have authority, but they aren't really justifying that authority yet. They don't implement a policy that protects themselves or anything like that. And so the idea is either we can fix those programs so that they defend themselves, they satisfy properties of protecting their own integrity, or maybe we have designate some other enforcer to protect those parties. And so we use the tool to do that manually currently, but once we have the set of constraints that make the system safe, we can generate these DIFC policies directly. And we're planning to generate the constraints automatically. So we have some ideas for doing that. And there are some other issues with between the layers that we're dealing with also. So we have some results. This was all generated manually. So I shouldn't go into this, right? Okay. All right. So the idea is, so I showed you browser first, but this is a web server. We've done a lot of analysis on a web server system. The idea is that the SpongeBob with the Dunder Mifflin is the web server. And this other SpongeBob on the right, you can think of as the kernel. I had a lot more slides with SpongeBob, but I didn't include those, I'm afraid. And so we don't trust the web server application to protect the integrity of our kernel. Right? I mean, we've looked at web server applications in great detail. They have a lot of interfaces that receive untrusted data. They have a lot of code from a lot of different parties all patched together. And they are too complicated really to put the integrity of the kernel in their responsibility. So what we need to do is find some components that will prevent the web server from being able to attack the kernel, being able to launch some of these local exploits. And basically what we need, and what these Batmen represent besides defense, is a cut. So we're mediating the flows between SpongeBob and the kernel by cutting the possible information flows between them, hopefully using the processes that have that are most likely to have integrity protection. So what we might show, well, what we have is some statistics that can show you how many untrusted interfaces each of the programs that you've selected are. But we want to keep digging into integrity properties of these programs and give you a more accurate view of why it is this particular cut is the best one, and how that would protect your kernel. So we manually picked some processes that we thought would make sense. And so we had to pick about 12 other processes, actually, on a web server system to protect the kernel, which is quite a few, actually. You know, you're thinking, okay, the web server is there, and maybe we can do a few things, and you'll be okay. No, they're actually with a minimum, well, not a minimum, it was a manual cut, so I don't know if it's a minimum or not. But coming up with what seemed like a reasonable cut still took about 12 things. And so that's a lot of code to trust your kernel with. So there's some work to be done there. So I claimed earlier that we could generate DIFC policies, and if you'd seen them and you knew what I was talking about, you would probably have jumped up and screamed, "No way," because these policies they can be very complex. I believe DIFC is even more fine-grained than SE Linux, for example, which has tens of thousands of rules for a Linux system. So these policies are not easy, but what it turns out is once you get the system configured, you can just generate the policy directly because our model corresponds to the DIFC model. We're generating proofs as we speak to show that the DIFC model is equivalent to our model. If something is safe in our model, it's safe in DIFC, and vice versa. And so then we can just produce the policy directly from whatever it is we create, which is, I think, kind of cool. Because even in their paper, if you were to look at it, they only had 3 components in their paper, because even specifying that was complicated to do manually. So this is a big challenge. So we have, let's see, so the tool, the Hippocrates tool that I was telling you about has a lot of things built in Prolog right now. We're porting some of them over to C, but to do analyses of individual VMs takes about tens of seconds with using SE Linux policies. I think if we get everything re-implemented in C now that we know what to do, it'll be pretty fast, just a matter of seconds to do the whole thing. So getting back to the beginning, we were talking about programmers and OS distributors and system administrators. I'm almost done. And what are they going to do? So the idea is we want to assign responsibilities to them. So we'd like developers to design their programs with some idea of what kind of attack surfaces they expect. So rather than just designing your program and hoping for the best, or really being vigilant and saying, okay, well, I'm going to protect every interface equally, which is very expensive and difficult to do. What we'd like to do is have them dictate, okay, these are the interfaces that I'm expecting to receive untrusted stuff. And so I'm going to do some work here to defend these interfaces. And these other interfaces, I'm expecting good stuff. And so if you give me bad stuff, you're going to be hacked probably. And so you shouldn't do it, Mr. OS Distributed. So the developer will develop something that and have tools to help them test that their work is corresponding to some attack surface. Then the OS distributors can use that to develop the whole system, so they can put these programs together and configure their policies such that they're not allowing these kind of attacks to occur. And then the system administrators could test when they put all of these systems together and they deploy the network policy that the overall system corresponds to the set of attack surfaces that they expect. So I haven't talked about this sort of work. There's some separate projects that we have that are looking at trying to make some of these things happen, and then we'll configure it together with the work that I discussed. Okay, so the premise is that host security, particular integrity, is an ad hoc endeavor. We can do a lot of good things, but we don't yet really know what they all mean in terms of integrity protection in a comprehensive way. So we want to come up ultimately with an approach where we can, and I'm using accurately here, sort of, we still have a ways to go in terms of gathering all the information we need to make things really accurate. But we want to be able to comprehensively and ultimately accurately reason about things. And so what we'd like to do is build a model where we can reason as accurately as we can today and hopefully improve our accuracy over time and focus on tasks that will help security community build tools for programmers and system administrators, OS distributors to use that will continually improve our security rather than sort of being one-off attacks and defenses of individual programs. Okay. So I'd be happy to take questions. Thanks. Okay, thank you all.